A couple things off the top before we jump into material. The exam Monday, I'll have a Z table, T table printout, as well as the formula sheet for you. I think I accidentally uploaded an older formula sheet on, or the one I originally thought we were going to cover through the material. So the PDF version, you don't need any of these formulas. We haven't looked at those. Just kind of the one that you'll get on the exam will be that Word version that's up there. I thought I resaved the PDF, and maybe I did. I didn't check Canvas. I just noticed when I opened it up this morning that it looked different. So I thought I had saved over the old version, and maybe I didn't. So your kind of Word document will be the one that's what you'll be getting on the exam. Okay. So you kind of notice here, we've got our test statistics equations kind of in that upper right corner. We haven't talked about this one. We'll talk about it today. We'll use these to do our hypothesis testing. You know, this is a lot, some of the older stuff, just kind of reminding how do you turn sample proportions into Z values? How do you turn sample means into Z values? All the way back to kind of just if we had normal distributed data, how do I turn values for that random variable X into Z values? Okay. So we'll do the final kind of hypothesis testing examples today. It's really not going to be any different. Like the procedure is going to be the same. So we'll just get more practice kind of looking at these left, right, and two-tailed tests. Okay. And I'll talk a little bit more about the exam. I want to make sure we kind of get through these before we kind of start to do a little bit of review and stuff. So the steps are exactly the same. We can use either the p-value or the critical value method. So up here, I've got the steps in terms of the critical values. It's going to be more likely, it's actually definitely what I'm going to do is I'm going to give you examples on the exam where you're finding the critical values for the student t distribution. And when we work through these problems, we'll kind of see why it's a little bit easier to do the critical value approach as opposed to the p-value approach. Okay. So everything looks exactly the same as what we were doing before. So if we kind of remember what we had before when we had our standard normally distributed variables, we'll take the sample evidence we found, subtract that assumed true population parameter, in this case, the population mean, divide by the standard deviation, right, of our sample statistic we're looking at, or the sample mean. Here, similar idea for the sample proportion. So we looked at all this last class or last couple classes, right? And we said we're calculating these Z statistic or these test statistics. It's still following the same format, right? We'll take whatever sample statistic we're looking at, we'll subtract the assumed true statistic, and then what's in our denominator always represents the standard deviation of whatever. Sorry, I wrote this wrong. The standard deviation of whatever statistic that we're talking about. Okay. It's the same process every single time. The only difference that we're going to have if we only have a sample variance, it's the exact same equation, right? I take my sample mean, I subtract the assumed true mean. It's just now the notation is a little bit different because the standard deviation of my sample means was calculated not using this known population variance, but using this sample variance, right? But once I plug the values in, these will look no different, right? It's just that I'm only using a sample variance, which lets me know, just like with confidence intervals, I need to use that student t distribution or distributions, right? How do I figure out which student t distribution I'm using? That degrees of freedom, right? So just n-1. So same rules will kind of apply as we did for confidence intervals.
Yeah, well, is this like type of test? Does it mean like
so remember, we have left or less than, greater than, right tail, not equal to, two-tail test. Yep, those are our three types of tests we can do. And they kind of change which side of the distribution we're looking at, or when we're calculating p-values or finding critical values. Remember, for the two-tail test, we have to now remember evidence on either side could go against that null. So let's kind of work through an example. So let's say I've got this kind of home price data, and I want to test for whether or not the average home price in Muncie is different than 90,000. So the first thing that I'll do is kind of identify what's my alternative hypothesis. That's what I'm trying to find, what I'm trying to test for. So I'm trying to test for whether or not it's different than 90,000. So what would my alternative hypothesis be? Yeah.
It's still not equal to.
Yep. So is that true population mean, mu, not equal to 90,000, right? Or is it different than 90,000? So what do I do for the null hypothesis? I assume the exact opposite is true and stack the deck against myself. Right? So I've now got, and I'll kind of get rid of this since we no longer need it here. I need a little more board space. So I've now am thinking I've got these sample means. They're going to be normally distributed around, if what I assume to be true was in fact true, they should be normally distributed around that population mean of 90,000, right? So, right, we've identified the normal alternative. What type of tail test do we have? Yeah, not equal to or two-tailed test, right? So evidence on either side could go against that assumed true value of 90,000. So what did I find? Looks like I found a sample mean of 85,000. Right. Now, if I'm interested, okay, how likely was it that I saw the sample evidence I did that was as inconsistent with what I assume to be true or anything more inconsistent? I can kind of think about the area in that left tail, right? To the left of 85,000. However, it would have been equally as likely for me to see a sample mean value, just to kind of make this clear, of 95,000 on the other side. And that would have been just as inconsistent with what I assume to be true, and it would go against the null, right? With a one-tailed test, evidence on the other side supports the null. So that's why we don't factor it in. But now evidence or sample means over on the other side that were equally as far away from that assumed true value of 90,000, those would also go against the null. So we have to remember, I'm going to find the area in this tail, but then the last step I'm going to have for a two-tailed test is I have to multiply that by 2. Yep. So what's the next step? I said it's kind of easier to do the critical value approach here. Now, it doesn't really matter. You can switch these steps. You can do the test statistic first and then the critical value. I think it makes it a little bit easier to find the critical values first, plot those, and then plot your test statistic to see if it's in that rejection region. So let's think about kind of what we're doing here, and I'll give you the visual. Try to give you the visual for all of these, right? So with our student T distribution, it's very easy to look up critical value. And I'm also going to show you how with that student T table, you can make finding the critical values for standard normal distributions easier as well, right? You don't have to look up 0.1 in the middle of the table, find that Z value. 0.05, find that Z value. 0.01, there's an easier way we can do this, right? And I'll kind of mention that once we go to the table. So if I want my critical values for our kind of 3 benchmark alphas, 0.01, 0.05, and 0.1, I'm going to have to use my student T distribution, right? Because I only have the sample variance. If you go back a slide, I believe we said the sample size was 51. So what would my degrees of freedom be? Simply n minus 1 or 50. Okay. Now, right away, I should be able to identify what set of critical values is correct here. If I've got a two-tailed test, which of these has to be the correct answer? Yeah, right? Because at every alpha, we're going to have a pair of critical values now, because evidence on either side could go against the null. And remember, the critical value tells us, like, if I see evidence that's any number of standard deviations further away from that assumed true value than this cutoff, this critical value, then I'll reject the null hypothesis. Well, now I need a cutoff on either side because evidence on either side could go against the null. So kind of think about, I know the answers here. I'll show you how we find them in a second, but I'm just going to plot them here to kind of make it a little bit easier. So we've got what? negative 1.68, negative 2.01, and negative 2.68. And then on the other side, we would have those same values, but positive, right? And now when we're drawing kind of those arrows into the tail for our rejection region, just to kind of give us that nice visual, it's going to look something like that. Yeah.
Negative 2.68.
Did I write these backwards? Yeah. I'm kind of writing them out. So this is right. You're right. Sorry about that. Right. We're just plotting these. I got carried away, just kind of looking at the values to make sure I had them right, not thinking about what order I was writing them in. So, because I think the way I had it here, right? 1, 5, 10% level. So the critical value first that I'll look at, that corresponds to the alpha 0.01 and so on and so forth. So I've got my rejection regions here. The next thing I need is my critical value. But how did I find these exact values? Here, it was easy because I could rule everything else out. But if I go to my student T table here, and I know that the area I want in the tail, remember alpha is 0.01, 0.05, and 0.1. The problem is for a two-tailed test, that means that I've got a total of alpha in the tails. So how much is in each tail? Alpha over 2. So it goes back to just like we were doing confidence intervals. So if I had the alphas of 0.01, 0.05, and 0.1, the values that I want in the tail, or that probability I want in each tail, is going to be half of that. So 0.005, 0.025, and 0.05. So those are the values I'll need to look up in that student T table, right? After I divide alpha by 2, that's the area I want in my tail. Okay. So I go to the 0.005, 0.025, and 0.05 columns, right? Those were the 3 areas I wanted in my tail, alpha divided by 2. I then scroll down to a degrees of freedom of 50. So the 0.005 column, if I round it to the second decimal, 2.68, right? Which I think is what I kind of have up here on the board or had in the previous slide. 0.025 column, 2.009 or 2.01. And then 0.05 column, 1.68 if I round to the second decimal. Now on the exam, I'll keep everything out to the third decimal. I was just kind of truncating it there to kind of make it a little bit easier to look at on the slides. But you can grab these 3 critical values very quickly, right? Just one process. I know the 3 alpha values I want. Well, I know I need to look up the area I want in the tail. So for a 2-tailed test, that's half of alpha. So I then just look up those 3 alpha divided by 2 values, 0.05, 0.25, and 0.05 at that degrees of freedom that I've got, which ours was 50, and I can quickly get my critical values. Now, once I find those values, I have to remember that I don't just have the positive one, but I've got a pair, right? It's those 3 values, but I've got positive and negatives, right? A pair of critical values at every single alpha. Any questions about how I'm using this student T table, how I kind of looking up these critical values here? So it's just like when we were looking up those values for a confidence interval, right? We look up the area we want in the tail for a 2-tailed test, that's half of alpha, and then go down to our degrees of freedom. Okay. So what's my next step? Well, I've got these critical values plotted, right? I know what they are. Look them up in the table, but I need to know what my test statistic is. Right? Does my test statistic fall in these rejection regions? I don't know exactly where 85,000 is going to be. So if I'm looking at these, just guessing, if I calculate the standard deviation of my sample means here, right? What's in my denominator? 100,000 divided by 51, and then 100 million, my sample variance, divide by 51, take the square root. Forget exactly what that ends up being, but my guess is that I'm 5,000 away from what I assume to be true. I doubt that's just 0.002 of a standard deviation. Could be. I don't know until I calculate that standard deviation and see what it actually is. But my guess is that being 5,000 away is probably not going to be just barely, like a 0.002 of a standard deviation. That seems very unlikely. Now, I also know my test statistic, or I'm not calling it a Z statistic anymore. So test statistic is kind of like a general term. Before, for sample proportions, and when we knew the population variance, we had Z statistics, right? Because they were coming from that standard normal or the Z table. Well, now we're calculating what we'll call just a T statistic. It's still a test statistic, but it's a T statistic because it comes from the student T distributions, right? So all that ZT stat, like Z statistic or T statistic, that's just identifying it's a test statistic coming from this distribution, okay? So just a little bit of terminology difference. You can always kind of just use the term test statistic, and it doesn't matter what example you're looking at, you'll be thinking about this correct. Okay. So I need to turn this in. It's just a matter of plugging my values in here. All right. So I go back to that old test statistic equation. I plug in that sample mean of 85,000, the assumed true value, which comes from that null alternative, which we said was 90,000, being different than 90,000. 100,000 is my sample variance. My sample size is 51. Now, I think I forgot to ask this, but like we know for sure that we could rule out A here. Why? My test statistic has to be what if it was below that assumed true value? Negative. It's going to be a certain number of standard deviations below that assumed true value. So sure enough, once I plug these in, I find negative 3.57. If I plotted that, it's going to be way out here in that left tail, very clearly in the rejection regions, rejection region at every single alpha here, right? Or every single significance level, or with every single level of confidence that we want to look at. 90, 95, 99% confidence, 10, 5, 1% significance, or alphas of 0.1, 0.05, 0.01, right? Those are all kind of saying the same thing, okay? So when I'm asking you these on the exams, with the practice exams, I'm going to be asking you about the significance levels, right? So what levels of significance can we reject at? Here we would say we reject at all three, right? Because we found sample evidence that was 3.5 standard deviations away from what we assume to be true. So what we assume to be true probably isn't true, because that probability is very, very small. Now, I'll kind of show you the problem where, what if I wanted to apply the p-value approach here? Well, instinctively, right? If I'm 3.5 standard deviations away, what is the area to the left of that test statistic pretty close to? Yeah, it's 0, right? Being 2 standard deviations away is pretty far, but being 3.5, we're very far away, right? So I could estimate my p-value is going to be pretty close to 0, which would be less than all 3 of my alphas, leading to the same decisions as I use the critical value approach. The problem is I can't find exactly what the p-value is from our table. After the exam, we'll look at how we do this in Excel. We can show that we can get the p-value very easily in Excel. The problem is with our table, notice that if we're looking at a certain degrees of freedom, I only have, what, 6 t-values I can look up, right? 0.849, or 1.2299, so on and so forth. 3.57, now, remember, the student t-distribution always looks at the right tail, but it's a symmetric distribution. So even though I have a test statistic of negative 3.57, the area to the left of that would be the same as the area to the right of the positive value. Problem is 3.57 isn't on this row, right? And that's because the probability is going to be really small. So I won't make you do this on the exam, but maybe after the exam, kind of for the next type of hypothesis testing, if we're using that student t-distribution, we have to use these tables instead of integrating these by ourselves, which no one wants to do. All I can really say is that, well, look, I know that the area to the, where was it at here? Right of 2.678 is 0.005. So the area to the right of 3.57 would have to just be less than point. That's all we can really say. We can just kind of put it in a range. Now, if we're using Excel, that doesn't matter. We have a function that will look up any test statistic for us, and we can find that p-value. So when it comes to this exam, you're dealing with a problem that has these sample means, and you only know the sample variance. There won't be a multiple choice question where I ask you for a p-value for those, right? So that might be a good indicator that, like, anytime you're asked for p-values on this next exam, should be using the standard normal distribution, right? I'm not going to kind of force you to. Now, I might ask you to find critical values, right? We can do that with the columns that we have, because I'm always going to use those same 3 benchmark alphas. So when it comes to these sample variance problems, kind of just using that critical value approach is always going to be easier if we're doing these by hand and using these tables. Once again, in Excel, p-value approach is just as easy as the critical value approach. Okay. So what else do I want to say? Okay. Any questions over anything before I kind of jump to this next thought? Is this, I don't know, we're starting to kind of see like this is a similar process. Hopefully it's all kind of looking becoming a little bit more familiar. I know there's a lot of moving parts. It's not lost on me. So one thing I wanted to mention was that if I did have other problems like sample proportion examples where you should use the standard normal, well, there, when I had alpha or even alpha divided by 2, I had to find the value that's closest to it in the middle of the table, find the course. I had to look up 3 of those like that. It's a little bit time consuming, especially for an exam where you've got 50 minutes. So a really nice little shortcut is, where else can I find the standard normal z values? Remember, we said this last row of our student t table, if we ever had an infinite population, that would just be our standard normal distribution. So I can use this table in the same way. Let's say I had a sample proportion example. Let's say it's a right tail test. So I want an alpha of 0.1, 0.05, or 0.01 in that right tail. I can use the student t table, look up those 3 areas I want in the tail, those 3 columns, from this very last row, and I can actually get the standard normal values out to the 3rd decimal. You don't even have to do this kind of rounding where I choose the higher of the two if I'm in between two. And I can get them all very quick, all three very quickly, right? 2.326, 1.645, 1.282. So if I'm asking you for critical values, a really easy way to kind of do that for even for your standard normal examples is use the last row of your student T, right? Because it's kind of like that last row isn't really a student T distribution. It's just kind of showing you like the comparison numbers to what you would have if you had a standard normal distribution. So it's almost like it's just taking only 6 values from your standard normal distribution to show them to you kind of as the comparison for all these other student T distributions of these different degrees of freedom. Okay. That's too confusing. You can just use the standard normal and look up those alpha values, but it's just you can save a little bit of time if you use that last row of the student T because it just is reflecting what you would find from that standard normal distribution. Is that clear what I'm saying? Are there any questions?
Can you show that in the Z table while I compare?
Yeah. So if I wanted an alpha of 0.1, how would I do that from the standard normal table? Well, my area in the tail is in the middle, so I'm looking for what's closest to 0.1. I'm in between these two values, so negative 1.28 and negative 1.29. Now, if I had a right tail test, I shouldn't have been looking up 0.1, right? I actually wanted 0.1 in the upper right tail. But I could have looked up alpha and then just remembered, oh, it's the same value for a right tail test, but positive, right? So 1.29. Well, notice with that student T table, I can actually be more precise. I was in between 1.28 and 1.29, but the actual Z value is 1.282. Right? It's not smack dab in the middle, so it's going to lean a little bit more to one of those values. So I can use the standard normal table to get it to that second decimal, and that's fine, right? But I can also use this last row. And the reason why it's easier is that if I'm only looking at one alpha, it's not that much easier. But I want to look up 3, a lot easier to just use this last row of the student T table. Is that, I'll kind of connect the two a little bit. Any questions on that? All right, so let's look at another example. So let's kind of look at this. So here I've got what? I'm trying to test for whether or not the birth weight of babies born to mothers who smoke while pregnant is less than this national average of 3,287, right? Seems like a pretty reasonable thing that I might want to test for, right? So here, what I want to test for is my alternative hypothesis. So my alternative hypothesis would be what here? That true population mean is, yeah, just less than 3,287, right? Whatever I'm testing for, that's my alternative hypothesis. The null is the exact opposite of that, or that it's greater than or equal to 3,287. So one way, it's maybe a little bit, I can see how you might flip the signs here, but you never should have answered A or B. Or first of all, I just repeat the answer. But if I get a not equal to sign in my alternative hypothesis, what kind of keyword am I looking for in a problem to identify that there's a two-tailed test? I said this terminology of being different than, right? That tells me different than is not equal to. I don't have that here. I want to test for whether it's less than, right? So I'm very understandable that I understand how maybe you accidentally switch your signs for being less than or greater than. It could just be a mistake that happens, which is maybe why there will be a short answer at the end of the exam. So if you do something like that, I can tell that you were close and give you some partial credit, right? So that short answer portion of the exam at the end will be kind of like 4 questions, but all one question, 4 different parts. It'll be hypothesis testing. So you'll identify the null alternative. You'll figure out what your test statistic is. You'll find your p-value or critical values. You'll then kind of make your rejection decision based off of either the p-values relationship to alpha or your critical values relationship to your test statistic. Okay. And provide support for that, right? You can't just tell me reject. That wouldn't be okay, it's why we reject, right? And we would say there, just to kind of digress a little bit, we reject if the p-value is less than alpha, and you could draw out the rejection regions if you wanted to for the critical value approach, just like we did. Or if you want an equation to kind of have to remember here, if the absolute value of, and it will depend on the example, but either your Z or T statistic, right, whatever your test statistic is, if the absolute value of that is greater than your critical value, then we reject as well, right? We can kind of use either method there. Right? Now, like I said, it might be a little bit easier to kind of plot those critical values and think about kind of drawing those arrows in the tail and then plot your test statistic. Does it fall in either one in any of those regions? But if you wanted kind of an equation, that would be kind of what that's saying. Yeah.
Would plotting it count as proving it?
Yeah. Yeah. If you show that kind of like you draw the arrow, rejection region, show your test statistics in the rejection region, that's fine. Yeah. Any questions on this before we keep moving here? So we've got what type of tail test? What signs in my alternative hypothesis? Left tail, right? Left stand sign. Only evidence on the left side of the distribution would go against the null. Because anything on the right side, right? Anything greater than or equal to that 3,287, that supports the null, right? So we've got this left tail test, right? I'll just kind of draw it out. I think drawing it out is really going to help. You don't technically have to, I guess, if you can visualize this in your mind, but I think it's to make it a lot easier. So here, my assumed true value comes from that null and alternative hypothesis. So it's that national average of 3,287. I then want to say, okay, I took this sample of 400 births. Oh, actually, I think I said, well, smoke while pregnant. I changed this was for some different variable, which was whether or not alcohol was used, right? So I found that the sample mean was 3,132. Right? Now, for a left tail test, if I wanted the p-value or the probability I saw sample evidence as inconsistent with what I assumed to be true or anything more consistent, it would just be the area to the left of that value. Okay? I already kind of mentioned, though, when we only have a sample variance like we do in this problem, it's difficult to look up those p-values. But if we just, I'm just trying to, we had a problem where we could, we're looking at the standard normal distribution and thinking about p-values. I'm just trying to make these complete to kind of show that we could look it up. Okay. So if I have a left-tailed test and I'm thinking about my critical values, which of these has to be the correct answer? Yeah. Yeah, right. I'm going to have negative critical value, or sorry. Yeah, negative critical values. Right. I'm looking at the left side of that distribution. The distribution is centered around 0. Every standard normal and every student t distribution is centered at 0. Just that student t's are a little more spread out. So I know that I'm going to have negative critical values. Okay. So right away, I can rule everything out. So I know what these are, right? So negative 1.28, negative 1.65, and negative 2.33. Now, this is a unique example. I won't give you one like this on the exam. I just want to kind of point out another limitation of our standard normal table. Right? Sorry, not our standard normal. A limitation of our student t table, right? So if I'm looking here, I can't find a degrees of freedom of 400, right? Once I start to get to these higher degrees of freedom, I start getting these kind of larger jumps, right? So I could kind of choose whatever's closest to them, look up those 3 alphas that I wanted, and kind of if I round those to the second decimal, that's where I was coming up with that 1.28, 1.65, and 2.33. On the exam, I'll only ever give you a degrees of freedom that you can exactly find that row on the table, right? So I wouldn't give you one where I give you 400. I would do something where I say like, assume the sample size was 500. That way you could find that exact row. But you'll notice to the second decimal, even at a degrees of freedom of 500, I'm only off at like the third decimal from my standard normal values, right? We said as we get higher and higher degrees of freedom, these student t distributions are a closer and closer approximation to the standard normal. So that's why to the second decimal, the values don't look any different, right? They both round to the same second decimal here. Okay? So these might look like the values you would find from your Z table, your standard normal distribution. It's just that they're a little different, but not past the second decimal, right? They're different to the third decimal. Okay. So I won't give you one that's like that confusing in the exam. I'll kind of even almost guarantee I won't give you a degrees of freedom over 80, right? So that'll be kind of make sure that the values are looking different enough from that standard normal distribution values. Okay. So how did I find those though? Let's assume that I was just choosing that degrees of freedom that was closest, or 500. So I go up here. The area that I want in my left tail, or alpha, is 0.1, 0.05, and 0.1. Problem is the student t-table always looks at the area to the right, or just kind of looking at those positive values, 1.28 to the second decimal, 1.65, 2.33. Those will be the values that are my critical values. I then need, that's why identifying the type of test is important, because I can look up and find those values in the table, but I have to remember those are going to be negative, right? Those same three values, but negative because I'm have a left tail test. I'm looking at the left-hand side. Okay. Questions on that before we keep going? Just making a little sense here. So it could be helpful once I finally get to my rejection decision, even if I plot these, to think about what level of significance they're associated with. So just right underneath kind of your critical values, maybe 1, 5, 10%. So you can kind of see that these are going to be the significance levels that correspond to these specific critical values. The next thing that we need is what? I've got my critical values. I can plot them. I need to calculate my test statistic, in this case, a t-statistic, right? From that student t-distribution. I'll have that formula on the formula sheet, right? It's up in that upper right corner. It's just a matter of plugging our values in. We have the sample mean of 3,132. We've got the assumed true mean of 3,287. We had a sample variance of 439,000-ish, and our sample size is 400. It's just a matter of plugging those values in there. Yeah.
I don't know when they use the Z chart and the T chart.
So, I already have those erased. Not erase this stuff, or you have to erase this around. We have three types of problems for both confidence intervals and hypothesis testing. Your student t-distribution, right, is when you're looking at all you have is a sample mean, and you only have a sample variance, right? You're trying to build a confidence interval where you're trying to hypothesis test against some true value for the population mean, but all you have is the sample variance. If you had a sample mean calculated and somehow you know something about the production process, like we said, these are unique examples, but somehow I know the population variance, then I can use that standard normal distribution, because in calculating that, I wasn't dividing by n-1. And then we also said for sample proportions, right? When I was calculating my test statistic, it looks something like this, right? So anytime I have sample proportion values or sample means with a known population variance, whether I'm doing hypothesis testing or confidence intervals, I use that standard normal. Anytime I've got a sample mean with only a sample variance, right, to calculate the standard deviation of my sample means, whether or not it's confidence intervals or hypothesis testing, I'll be using the student t. So three different types of examples. I mean, if it were me, I think like this is something that not necessarily you guys, but I see incoming people coming out of high school not have this skill, which I feel like should be something that's taught very early on. Right, I would use context clues. Right, it's like if you don't know what a word is, right, you look for context clues of what the person is talking about. Just like here, if I come down sample proportion, I'm giving you the notation. Sample proportion, I should match that up to the formula sheet. The formula sheet is even pretty kind in that it uses Z or T, right, to identify, where's my confidence intervals down here, to kind of match up with that notation. So look at the notation that's used, right? Even if you can't remember that P hat is the sample proportion, on the exam it will say the sample proportion is P hat is equal to this. So that way it should be a little bit easier to kind of match up to what formulas you should be using there. Right? Also, CI here, confidence interval equation. If you get to a problem and ask for a confidence interval and you look at any other formula other than this, it's not good. I can't help you with that. I mean, these are the only equations you should use. Now, you might use the wrong one. I understand that, but like confidence interval, like use those context clues to match up, at least limit write yourself down so you know at least the structure of the formula that you're looking for. Now, if you mix up that you have a sample variance instead of a population variance, I understand that that's harder, right? It's reading a little bit more careful. But even there, right? I look at these practice exams. I shouldn't have said that. I was kind of mean, but you know, you shouldn't be making these mistakes, hopefully, at this point. Oh, I don't know if I have an example like here. Maybe on practice exam B. I've got one to point this out. All right, so I'll probably be a little bit kinder. So even if you don't use, so one thing that you might have to know, even if I don't use notation, is that your sigma is your population, right? And then S is just representing the sample, right? That goes going way back. I will probably be kinder than I was in the practice exams and say the population variance of 15, and then next to it, right, sigma squared is equal to 15, right? So even there on the exam, I'll probably be a little bit kinder than when I was writing these quick practice exams, where I'll kind of use more notation as well to just kind of assist with kind of connecting to those formulas. Does that make sense what I'm saying there? Yeah, getting a little bit of confused, so I'm going to. All right. So we still have to finish the other problem, right? But we're pretty much done. So we've got this test statistic of negative 4.6. Once again, I mean, as we work through more of these examples, we're 4.5 standard deviations away. That p-value is going to be pretty close to what? Yeah, pretty close to 0. So if I'm thinking about my 3 alpha values, 0.1, 0.05, and 0.1, if I've got a p-value of basically 0, I'm going to be less than all 3 of those. I should once again be able to reject at every single level. All right. Same kind of idea. The critical values, if I plot negative 4.6, excuse me, against those, I'm very clearly in the rejection region for every single level. Right. Now, in practice, this might get a little bit trickier, right? Because we just worked through 2 examples where the test statistic was extremely large, right? Well, what if it was instead, I don't know, 1.8, or sorry, negative 1.8. Well, there it's a little bit trickier, right? Because now if my p-value, right, we're trying to test to see whether or not my p-value is less than alpha. If I had a test statistic of 1.8, negative 1.8, I can't exactly find my p-value from that student t-table, right? Because even if I go to that degrees of freedom that was closest to 400, which was 500, I can't find 1.8 here. Now, it's in between these 2 t-values, which would correspond to what? 0.05 and 0.025. So I know my p-value is somewhere in that range, which if I know that it's somewhere in between 0.25 and 0.05, I actually know that that has to still be less than 0.1. It would have to be less than 0.05. It's kind of built in there, but it wouldn't be less than 0.01. So I could reject at the 10 and 5% levels, but not at the 1%, right? Or I could reject with 90, 95% confidence, not with 99. Now, I'm not going to make you do this on the exam where I give you a p-value that's in between. If I did ask you for a p-value from an example where you only had a sample variance, I would like give you an assumed true test statistic. So I think I do have an example of that. If we look at practice exam B. So a lot of the times I'll ask you for a test statistic, and then in the next problem, I don't want you to have cascading errors. So I say, assume the test statistic you found was this, right? I would give you an assumed true test statistic. That would be exactly one of these values. So maybe 2.334 or 2.586, right? So I still could expect you to find a p-value. I won't make you put it in a range. The only time I could expect that though is if I give you this assumed true test statistic, right? So it's exactly one of those values in the table. Okay. So that would be kind of the p-value approach. For the critical value approach, I'm in the rejection region for that 10% level, right? Where my test statistic was greater in absolute value than my critical value. It was greater than the absolute value of my critical value at the 5% level as well, where it was kind of plotted it was in that rejection region. But it wasn't quite in that rejection region for the 1% level, right? Where it was actually less than the absolute value of my critical value. Okay. When I say less than, we're taking the absolute value, right? So 1.8 will be less than 2.33. So same decisions, right? Doesn't matter which method I use there. Okay. Any questions on this one?
Say that again.
Yeah, so we had negative signs in front of here, right?
Yeah.
And I think earlier I said, if you wanted an equation to kind of know when you should reject, the reason why we're doing this is because for a left tail test, we're dealing with negative values. So if it's like negative 2.33 is larger than negative, it's actually less than. But if we're on the other side, well, then I have to change my terminology to be, well, now 1.8 would be less than 2.33.
1.8. That's what I missed.
That was just me coming up with another example. Yeah. No, that is, sorry, reiterate that when I'm saying this negative 1.8.
This one, they're all rejected.
Yes,
Okay.
this one.
Repeated.
Yep.
Yeah, sorry.
Yeah, I'm just saying if I gave you a little bit more of an interesting example. Yeah. So, what was I saying? Oh, but yeah, the reason why we use that absolute value is because then it doesn't matter if I've got a left, right, or two-tailed test, this will always work, right? It kind of drops that negative sign. You don't have to worry about what type of tail test you have. You just need to compare the magnitude or the absolute value of those. Okay. But like I said, it's probably easier to plot it. I don't know, but and I'll accept that as kind of justification. Any other questions, just conceptually or kind of broad questions? I don't think I have. I've got other examples for sample proportions or sample means that we could work through. But I think maybe it's more helpful to just say some larger things about the exam or just kind of ask you guys for questions going into it. So kind of already mentioned this about the formula sheet, but you've got your 3 different types of confidence intervals you could build. Sample mean, known population variance. So we use that standard normal distribution. Anytime you see, if you see a problem with the word proportion, I mean, you shouldn't do this because you might need it for other problems, but tear up the student t-table and throw it to the side, right? Proportion is synonymous with always using that standard normal distribution on the z-tables. And the confidence interval equation kind of reminds you of that, right? Then if I have a sample mean example where I only have a sample variance, I'm using that student t. I've got my 3 test statistic equations for those same 3 types of examples up here. And then this is going to be kind of just going back. So if you look at the practice exams, I've got it kind of just like the previous exam. It kind of flows with how we talk about things in class. So it goes all the way back to, I might give you just a normally distributed variable. I'll tell you the mean, I'll tell you the variance. And then ask you what's the probability you see it be above a certain value, maybe between 2 values, below a certain value. Well, you need to turn those values into z values, look them up in the table, right? Now, that z value equation goes back to if I have just a normally distributed variable, pretty easy, especially when I'm giving you a known population mean and known population variance or standard deviation. Now, those aren't practical or as practical, right? We usually won't have the information, but that was kind of starting. We need to know this was true in order to kind of build onto it. Like the process of what we're doing here is really remain the same. It's just that we're no longer looking at that normally distributed variable X. Once we get to hypothesis testing, we're looking at sample mean values. Well, then we know the distribution of sample means was normally distributed, so we could apply all the same things we did before. I'll take the sample mean I'm looking at, subtract the mean of that sample mean, which would have been the population mean, but we don't know that, but we're assuming it's equal to a certain value. So we can subtract that assumed true value. I just attribute the mean of my sample means, just like the population mean was the mean of the data, right? The random variable X. We then divide by, remember what this denominator represents in each of my test statistic equations is just the standard deviation of that statistic. So here, this is the standard deviation of my sample means, or I've got that down here in this formula. Right? On the left-hand side. So that's all that denominator represents. Well, that's what we were originally doing with just normally distributed variables. We divided by the standard deviation. It's just that we didn't divide by the standard deviation of sample means because we weren't talking about sample means. Right? So it's all following the same kind of similar process. What else do I want to say here? So you may not use all of these equations per se, but they are kind of good reminders of like, oh, here's the standard deviation of my sample proportions. That's what I kind of see down here. I'm dividing by for my test statistic. Right? Another thing I wanted to mention, and know that it was complicated. So there's a reason why it's not on here. I'm not going to expect you to know how to answer problems about the log normal or exponential distributions. Okay. So don't worry, don't study any of that. In terms of, I'm not going to ask you questions about those. Okay. We'll kind of restrict it to normally distributed variables. Then thinking about, okay, what if I have my sample means, right? So on the next problem, usually I use the same information. So we have this normally distributed variable. We're then going to take a sample from it. Now we're thinking about what does the distribution of our sample means look like? Ask you for probabilities being seeing sample means above or below or between values. Right? But it's still running from that same problem where you somehow knew the population mean. We'll then probably transition to the three different types of problems we could have when we don't know the population mean or population proportion, and we have to just build confidence intervals or do hypothesis testing for where the true population mean and proportion is. So here in this specific practice exam, we start out with sample proportion examples. I ask you to then do some hypothesis testing. I may also ask you to build a confidence interval on the exam for that. So know how to kind of build these confidence intervals, even though I don't think that was oh yeah, actually that was right here, right? It's called kind of use this information for from here all the way down, okay? I'll also, one thing I didn't do on these practice exams, because you can see the answer key, and if you did get the null alternative hypothesis wrong, you could figure out, oh, okay, it was supposed to be this, then how would I work the next ones? On the exam, if I ask you to identify a null alternative, the next problem, it's going to get a little bit annoying, but it helps you. I will then say, assume this was the null alternative hypothesis. And it might be using different values. The sign may be wildly different. It may be exactly what the null alternative hypothesis should have been. There's no rhyme or, well, there's rhyme or reason into why I'm giving you the assumed true values, but that rhyme or reason has nothing to do with what the correct answer was in the previous problem, right? So don't read into, don't try to like game the exam and read into those at all, because it could very much work in the opposite direction. A lot of the times I might be choosing something the opposite because it's more interesting than what the actual answer was in the previous problem.
And those critical values are going to be the same. It doesn't matter, right?
Yeah, I mean, we'll start seeing these pop up for the standard normal distribution. The critical values are always the same. Why do they vary for the student t? Because those values will Yep, those values will depend on your degrees of freedom. Yep. Any other kind of broad questions on the exam? Yeah.
Are the free response ones or peanut toss?
Yeah, so I mean, I can't tell you the exact, but it will be hypothesis testing.
Okay.
And it will be all of our steps. Identify the null alternative. I'll ask you for a test statistic. Find the p-value or critical values. I might even let you do either one, whichever you think's easier. And then I'll ask you, using whichever method you selected, how do you make, or what's the rejection decision at the 10, 5, and 1% levels?
Right.
Yep. So there'll be 16 multiple choice, and then the 4 at the end, which are all kind of like one problem of 4 parts, will be short answer. Don't think time should be an issue. But keep it in mind as you're kind of working through it. If you know that you are kind of, it takes a little bit longer to do the hypothesis testing one, those are going to be at the end, right? Any other questions? Are we feeling okay about this? I mean, probably not. I know we don't maybe understand 100%. I'll take that into consideration. It's maybe why I made a little bit more of a short answer to kind of give some partial credit. If you have any questions, I'll be around my office today. Actually, if you want to stop by, should be there from 2 to 4. And if I'm not there, I'll be back in a couple minutes. Other than that, if you have a question, feel free to shoot me an email even over the weekend. I will see you guys in class on Monday. Okay.